Okay, should I start, Kobe?
Yes, please.
Thank you very much. So it's really a great pleasure to be here, even though virtually, to participate in this fantastic program. And I will be part of the team of 4 instructors, together with Joan Bruna from NYU, Taco Coyne from Qualcomm, and Petar Velišković from DeepMind. Will be teaching this new course on geometric deep learning. And I will start with the first introductory lecture, where I will give an overview of the basic ideas that we'll be discussing in this course, and the overall structure of the course. And well, if you don't get some of the concepts in this first lecture, don't worry, because we will explain them in much greater detail further down the road. So if you wonder what at all is this geometric deep learning, this course will be about the fundamental principles that underlie deep representation learning and most of modern deep neural network architectures. And if you want just a single word to convey the gist of the course, it will be about symmetry and its different manifestations in machine learning. And really, if there is one big idea that I could highlight in science, or deserves to be highlighted in science, I think it is symmetry. And symmetry, as wide or as narrow as you may define its meaning, is one idea by which man through the ages has tried to comprehend and create order, beauty, and perfection. So these are the words of Hermann Weyl. He was one of the 20th century's best mathematicians and played a crucial role in creating the mathematical foundations of modern physics. And he wrote a book about symmetry. It's actually titled Symmetry, on the eve of his retirement from the Institute for Advanced Study in Princeton. And there he writes for a broad audience about symmetry, how it has occupied a special place in science and arts from the ancient times, from Sumerian symmetric designs to the Pythagoreans, who believed the circle to be perfect due to its rotational symmetry. And the term itself has Greek origin. Symmetria literally translates as same measure. And ancient Greeks used this term to somehow vaguely convey the beauty of proportion in arts and harmony in music. And for example, Plato considered the 5 regular polyhedra, what we now call the Platonic solids, so fundamental that they must be the basic building blocks that shape the material world. And I should say that this was not very far from truth. And it was the astronomer and mathematician Johannes Kepler, many centuries after, to first attempt a rigorous analysis of symmetry. And in particular, he was concerned with the symmetric shape of water crystals. And he wrote a book titled On the Six-Cornered Snowflake. It was prepared as a Christmas gift to his friend in 1611. And in this book, he had a deep insight. He attributed this six-fold dihedral symmetry of snowflakes to what is now called a hexagonal packing of particles. And it was an idea that clearly preceded the understanding of how matter is formed and the concept of atoms and molecules and crystals, but still it holds today as the basis of modern crystallography. So if you already mentioned ancient Greece, modern geometry is also traced back to ancient Greece and the seminal work of Euclid, the elements, and what we now call the Euclidean geometry. It was in fact the only geometry that was known for over 2000 years. And at the core of Euclidean geometry was a set of 5 basic assumptions, or how Euclid called them, postulates, that he used to derive certain properties and prove results. And for hundreds of years, the 5th postulate of Euclidean geometry, stating that it is possible to pass only one line parallel to a given line through a point that lies outside of it. This 5th postulate defied any attempt to prove it. People for centuries tried to prove it from other postulates of geometry. And what happened is, in the 19th century, this Euclidean monopoly came to an end. And the 19th century was really a remarkable burst of creativity that made geometry into probably one of the most exciting fields of mathematics. And first it was the development of what is called projective geometry. So it was the French Poncelet. He was an officer in the Napoleonic army. He participated in the hugely unsuccessful campaign in Russia. He got captured and imprisoned there. And apparently the Russian captivity was fruitful for him, because during these 3 years, between 1812 and 1814, he wrote a comprehensive treatise on projective geometry that was published a few years later. And in projective geometry, points and lines are interchangeable. And there is no such thing as parallelism, as any two lines intersect at exactly a point. And projective geometry is nowadays very popular in computer graphics, for example. So it is often not considered a non-Euclidean geometry, strictly speaking, but it was probably the first one to undermine this Euclidean concept of parallelism. So the first published construction of a non-Euclidean geometry is credited to Nikolai Lobachevsky, a Russian mathematician that considered the fifth axiom of Euclidean geometry a completely arbitrary limitation. As an alternative, he proposed a new one, that more than one line can pass through a point that is parallel to a given one, and such a construction required a space with negative curvature, what we now call a hyperbolic space. So sometimes this is called hyperbolic geometry. And this idea was so unconventional and heretical at the time of publication that he was openly derided by colleagues at his university for writing and publishing such nonsense. So some mathematicians of his time said that this is at the level of some school teacher, not a university professor. And it was also János Bolyai, an Hungarian mathematician that apparently came to the same ideas together with Lobachevsky, but published them a decade later. And he had an interesting correspondence that survived with his father, also a mathematician, who then reported them to Gauss. So Gauss was the mathematician of the time. In Latin, he was called the Princeps Mathematicorum, the prince of mathematicians. And Gauss himself replied quite a bit tersely, even though he was very generous with giving credit. And in his letter to Bolyai's father, he said that he himself considered the same ideas, but never really dared to publish them. And then it was Gauss's own PhD student, Bernard Riemann, who probably put the last nail in Euclid's coffin. And in his lecture on the hypothesis on which geometry is based, he basically formulated what is nowadays called differential geometry of surfaces, what we now call, after him, the Riemannian geometry. But he also constructed non-Euclidean geometry on the sphere, that is sometimes called the Riemannian geometry in the narrow sense. And in this case, the fifth postulate doesn't hold as well as in the construction of Lobachevsky, but also the second postulate doesn't hold, that all straight lines can be continued indefinitely. On the sphere, all straight lines have finite lengths. So as a result of all these developments in the 19th century, basically what happened is that an entire zoo of different geometries emerged, and towards the end of the 1800s, these became disparate fields, and mathematicians were debating which geometry is the right one and what actually defines a geometry. And a way out of this pickle was shown by a young German mathematician, Felix Klein. So he was only 23 years old when in 1872 he was appointed as a professor in the small Bavarian University of Erlangen. And he was asked, as it was customary, to deliver his research program. He actually gave a talk for the popular audience, and not, as the legend goes, it was not about his research program, it was more about teaching of mathematics, but he published a small brochure that entered the history of mathematics as the Erlangen Programme. And in this program, Klein proposed a very radical approach of treating geometry as the study of invariance and symmetries. So these are the properties that remain unchanged under some class of transformations. And this approach immediately created clarity by showing that different geometries could be defined by an appropriate choice of this symmetry. And for example, symmetries defining Euclidean geometry are rigid motions. So these are translations, reflections, and rotations that preserve properties such as angles, distances, areas, parallelism of lines, and their intersections. And the language that Klein used to formalize the notion of symmetry was the language of group theory. And it was also a new shiny mathematical field that was born in the 19th century. And the term group was first used by Galois. He was a French mathematician, actually probably one of the most brilliant mathematicians that died very young in his early 20s in a duel. And group theory is strongly associated with Klein and another mathematician that was colleague of Klein that worked together with him in Germany called Sophus Lie. And many notions in group theory are named after these two people. So they developed together some of the basic concepts of this discipline. And we'll talk about group theory more in details in the following lectures. So maybe as another historical factoid, even though the Erlangen University takes a lot of pride in this association with Felix Klein and his Erlangen program, he actually didn't stay there for long and eventually moved to Göttingen, which was the world's leading place for mathematics at the time. So that was the university where Gauss himself had worked. And he continued working on these ideas, and the impact of the Erlangen program and these ideas on geometry and mathematics in general were very profound. And it also spilled into other fields, in particular in physics. And AMMI Noether, she was Klein's colleagues in Göttingen, she proved that every differentiable symmetry of the action of a physical system has a corresponding conservation law. And by all means, this was really a stunning result because beforehand, you had to do very detailed, meticulous experimental observations to discover fundamental laws such as conservation of energy, let's say. So you would measure the energy in many experiments, and you will see that up to some small errors, the energy remains the same. And it was an empirical result, not coming from anywhere. So what Noether's theorem established is that the conservation of energy emerges from translational symmetry of time. So it's rather intuitive idea that the results of an experiment would be the same if you did it yesterday, today, or if you do it tomorrow. And Hermann Weyl, I cited his poetic definition of symmetry. He used these ideas to develop the concept of what he called gauge invariance, or the German term is Equivariance. So it was a principle from which electromagnetism could be derived. And he also speculated, he tried to unify it with gravitation. And curiously, history preserved his correspondence with Einstein that argued that this construction was beautiful, but not physically correct. And you can see a nice paper by Norbert Straumann that describes the early history of gauge theories, if you're interested in physics. But with the development of quantum mechanics, Weyl reinterpreted his concept of gauge invariance. It became very popular and enshrined in physics. And after several decades, in what is called non-abelian gauge theory, it was finally possible in a theory that was developed by Young and Mills in 1954 to provide a unified framework that describes all the fundamental forces of nature with the exception of gravity. And this is what is called the standard model in particle physics. And it unifies the description of electromagnetism, weak interactions and strong interactions using the language of group theory and gauge invariance. So it's, again, with the exception of gravity, it's all the physics that we know today. And I can only repeat the words of another Nobel-winning physicist, Philip Anderson, that it is only slightly overstating the case to say that physics is the study of symmetry. So just to give you an idea, so I have this big book written by Roger Penrose, a British mathematician at Oxford that recently won the Nobel Prize. So this is more than 1,000 pages, probably the most comprehensive attempt to capture the mathematical underpinning of modern physics. So if you were to distill these 1,000+ pages into one word, it would be symmetry. He devotes a lot of time to group theory, to the concepts of symmetry and how they are fundamental in physics. So this was an historical context, and you may wonder at this point, what does it all have to do with deep learning, right? So you came here probably to hear about deep learning, and so far I've been talking to you about physics. So the truth is that in my opinion, the current state of affairs in the field of deep learning reminds a lot the situation of geometry in the 19th century. On the one hand, of course, I think there is no doubt that in the past decade, deep learning has brought a true revolution in data science. It made possible many tasks that previously, maybe 20 years ago, would be considered nearly science fiction. Whether it's computer vision that powers autonomous driving, speech recognition that powers your iPhone, right? Natural language translation, sometimes already without supervision, playing intelligent games like Go, or doing protein folding. So on the other hand, we now have this zoo of different neural network architectures for different kinds of data, but very few unifying principles. And as a consequence, it's difficult to understand the relations between different methods. And this inevitably leads to the reinvention and rebranding of the same concepts. And you find yourself with the same idea that is presented and published in different communities under different names. Sometimes it also brings unpleasant and bitter fights over priority. So this is really an unhealthy situation. So we need some form of unification, and we want to do it in the spirit of the Erlangen Programme, and this is what we call geometric deep learning. And it serves two purposes. First, maybe from the pedagogical perspective, it provides a common mathematical framework to study the most successful neural network architectures that are currently used ubiquitously in this field of deep learning or deep representation learning. And second, this is really a mindset. It gives you a constructive procedure to incorporate prior knowledge into neural networks and build future architectures in a principled way. So if you ask what will be after deep learning or maybe beyond learning by backpropagation, the hope is that these principles will outlast their particular implementations. So this term, we popularized it in a 2017 paper in the IEEE Signal Processing magazine that I co-authored with Joan Bruna and others. And most recently with Joan, Taco, and Peter, we wrote a long article that is a preview of a book that we are currently writing on which this course will be based. And you can look, if you haven't done it yet, go to the website geometricdeeplearning.com and you can see this paper online. So let me give you a little bit of a motivation where actually symmetry and how exactly it is manifested in machine learning and why it is important. So if we consider the simplest setting of machine learning, supervised learning, this is essentially a glorified function estimation problem, right? So we're given some unknown function and we observe its output on what is called a training set. And what we try to do is to find a function that fits well the training data. And this function comes from some class of functions, some hypothesis class. And this way we try to predict the outputs on previously unseen inputs. So this is what we call a test set. So the typical example that is given is image classification. You have a set of dog and cat images, and it's a binary classification problem. You try to classify them into a class of cats and dogs. Okay. So what happened over the past decade is that two trends coincided: the availability of large and high quality data sets, such as ImageNet, that has millions of labeled images, together with sufficient computational resources, GPUs that originated as graphics hardware, but they're especially suitable for general purpose computations that you encounter in deep learning. And these two trends have led to the design of rich function classes that had the capacity, at least in theory, to interpolate such large data sets. And it appeared that neural networks are a suitable choice to represent functions. And neural networks, of course, are not new at all, right? So they are at least 70 years old. So the first works are from the 50s. And even with a very simple choice of architecture like the perceptron that I show here, this is probably the earliest and the simplest neural network, we can show that if we connect just two layers of such networks, what is called a multi-layer perceptron or a perceptron with one hidden layer, it produces a dense class of functions. Or in other words, we can approximate any continuous function or even broader class of functions to any desired accuracy. So we call this property universal approximation, right? So it means that this is a very general architecture that can represent practically anything, right? So this is a very well studied problem, right? So the setting of this problem, it is studied in approximation theory, and in low dimensions, we have a lot of results that tell us exactly how the error will behave if we sample, for example, our data in a certain way. So it has been studied very extensively over the past century or even more. But what appears is that the situation is entirely different in high dimensions. And again, we'll hear about it more in depth from Joan in his lecture. But what we can show is that even if we pick up a very nice class of functions, what is called Lipschitz continuous functions, And in this case, it's a superposition of Gaussian blobs that are put in quadrants of a unit cube in d dimensions. So what we'll find out very quickly that as the dimensionality of this space, of this unit cube grows, the number of samples will grow exponentially. So we get a phenomenon that is colloquially known as the curse of dimensionality. And modern machine learning methods need to operate with data not in 2 or 3 dimensions, but in thousands or even millions of dimensions. So think of images, right? They're extremely large. So these are very high dimensional inputs. So the curse of dimensionality is a necessary evil that accompanies every machine learning problem. So it makes such a naive approach to learning impossible. And this is probably best seen in computer vision applications like image classification that we already mentioned, because images are extremely high dimensional. Even tiny images from this AMMI data set, they are almost 1,000 dimensional, right? But if you look at this problem intuitively, you see that there is a lot of structure that if I just take my image and treat it as a vector, as a d-dimensional vector that I give as an input to let's say, perceptron, I destroy this structure, right? This local spatial connectivity between pixels. And as a result, now, if I take the image and shift it by just 1 pixel, this vectorized input will be very different. And the neural network will need to be shown a lot of examples in order to learn that shifted inputs must be classified in the same way. So this is a standard practice in deep learning, what we call a data augmentation. So if we don't know how to model certain invariance or certain way of telling that the shifted versions of these digits must be the same, we just add such examples to the training set. And this can be extremely wasteful. So in computer vision, the remedy for this problem came from classical works in neuroscience, in particular the Nobel-winning work by Hubel and Wiesel that studied the organization of the visual cortex, and they showed that brain neurons are organized into what they call local receptive fields. And this served as an inspiration to a new class of architectures with local shared weights. So the first precursor of modern architectures of this kind was the neocognitron of Fukushima. It's a paper from 1980, and it's really remarkable if you look at this paper, how many modern elements of deep learning are already contained there. For example, the activation function that he used was already the half rectifier, the ReLU, that is considered to be almost a hallmark of modern deep architectures. And obviously, this culminated in convolutional neural networks, or CNNs, the pioneering work of Jan LeCun. And there, the concept of weight sharing across the image effectively solved the curse of dimensionality and made CNNs invariant to object translation. So let me show you now another example. So what you see here is a molecule of caffeine. I believe we are all very intimately familiar with it. So I have it in my morning cup of coffee. And what is shown here is actually a graph representation of a molecule of caffeine, right? So here atoms are nodes and edges represent chemical bonds between atoms. So if we were to apply neural network to this input, for example, to predict some chemical properties like its binding energy or some other property, we can again parse it into a vector and give it to a neural network. But now what we see that we can rearrange the nodes in any way. Basically, we can permute the nodes of our graph, because in graphs, unlike images, we don't have a particular preferential way of ordering the nodes. And molecular graphs appear to be just one example of data with this irregular non-Euclidean structure on which we would like to apply deep learning techniques. And another prominent example are social networks. They're gigantic graphs with hundreds of millions of nodes and billions of edges. And we also have different kinds of networks in biology, such as interactomes or interaction networks, manifolds and meshes in computer graphics, which we'll be also discussing in this course, and many other examples of data which wait to be dealt with in a principled way. So let us go back to this example of multidimensional image classification that at the first glance seemed hopeless because of the curse of dimensionality. So what happens, fortunately, that we do have additional structure that comes from the geometry of the input signal. And we call this structure geometric prior, and as we'll see, it is a general powerful principle that gives us hope and optimism in dimensionality curse problems, and we'll see manifestations of these geometric priors again and again, and everything that we discuss in this course. And in our example of image classification, the input image is not just a d-dimensional vector. It's a signal defined on some geometric domain, I denoted by omega, which in this case is a two-dimensional grid. And I denote the space of signals by x of omega. Okay, so the structure of the domain is captured by a symmetry group that is denoted by G. So in this case, it's the group of two-dimensional translations that acts on the points of on omega. So again, this week in the lecture that will be given by Taco, we'll discuss in more details what groups exactly are and how they act on respective geometric domains. But what we need to understand here is that we have the domain, we have a group that acts on it, so it describes its structure, its symmetry, and the action of the group on points on the domain is manifested on signals defined on this domain through what is called the group representation, I denoted by rho. So to make it much more concrete, in this case, the representation is a matrix that acts on d-dimensional vectors. It's a d by d matrix that is, in this example, is simply a translation or a shift operator. Okay. Now, this geometric structure of the domain that underlies the input signal affects the functions that we define on the signals I'm trying to learn, right? So the functions we denoted by f. And we can have functions that are unaffected by the action of the group, what we call invariant functions. And a good example here is the image classification problem. No matter where, for example, the cat is located in the image, we still want to say that it's a cat. So it's an example of shift invariance. Okay, and on the other hand, we can have a case where the function has the same input and output structure. For example, in problems like image segmentation, the output will be a pixel-wise label mask. So we want the output to be transformed in exactly the same way as the input, or what we call equivariant function. So what we see here is an example of shift equivariance. So another kind of geometric prior that we can have in our problems is what is called scale separation. So in some cases, we can construct a multi-scale hierarchy of domains, for example, by coarsening the grid. And we have now another version of the grid that I denote by omega prime. And this coarsening assimilates nearby points on the domain and produces also a hierarchy of signal spaces that are related by what is called the coarse grading operator that I denote by P. And on this coarse grid, I can define a new coarse scale function that I denote by f prime. And we can say that our function is locally stable if it can be approximated as the composition of this coarse grading operator and the coarse scale function f prime. And while the regional function might depend on long-range interactions on the domain, in these special locally stable functions, it is possible to separate the interaction across scales. And if you again take the example of image recognition, this corresponds to applying a classifier at a lower resolution image. And these two principles give us a very general blueprint of geometric deep learning that we can probably recognize in the majority of popular deep neural architectures. We can apply a sequence of equivariant layers that preserve the structure of the domain, possibly followed by an invariant global pooling layer that aggregates everything into a single output. And in some cases, we can also have a hierarchy of domains by some coursing procedure that takes the form of local pooling. And this is a very general blueprint. It can be applied to different types of geometric structures and geometric data. And in particular, we'll see it on grids, on domains, what is called homogeneous spaces with groups acting globally in a transitive way, graphs and manifolds in the form of gauge symmetries. And this is what we call the 5G of geometric deep learning. So the implementation of these principles in the form of inductive biases leads to some of the most popular architectures that exist today in deep representation learning, whether it's convolutional neural networks, graph neural networks, deep set transformers, LSTMs as well, and intrinsic CNNs, maybe a little bit more exotic, that are used in computer graphics and vision. They can all be derived from fundamental principles of symmetry, same way as all physics can be derived from respective symmetries. We argue that the same principles hold in deep learning. So more specifically, the course schedule. So today, the first hour is this introduction. I will briefly overview without going into too much details. Then Joan will be talking about basics of machine learning in high dimension. Then Taco and Joan will be talking about the foundations of group theory, geometric priors. the concepts of invariance and equivariance and symmetry and their approximate versions. Then Petra will be giving 2 lectures on deep learning on graphs and sets, basically graph neural networks. Then we'll be talking about grids and groups, manifolds and meshes, gauges and bundles, sequences and the idea of time warping and how we can derive LSTM type architectures from these. And then we'll conclude with applications and some open questions and interesting research directions. So again, we'll be using the proto book that you can get from geometricdeeplearning.com. So here I refer to the respective sections in this book. And for the discussion on manifolds and gauges, there is also an excellent paper that was recently published by Maurice Weiler, where he, on over 200 pages, describes in much details the ideas of structure groups and fiber bundles and how symmetry can be used to create coordinate-free convolution-like networks on manifolds. Okay, so let me start with graphs. So I would like to showcase briefly some of these instances of geometric deep learning blueprint, and graphs are probably the most versatile and the most important constructions out of all these domains. They're really ubiquitous. We can describe practically any system of relations or interactions as a graph. And this is true from nanoscales, where we can model individual molecules as graphs that, for example, consist of atoms and chemical bonds, to microscales. We can look at different interactions between biological entities, molecules, drugs, proteins, and so on, right? What is called interactomes in biology. And all the way to the macro scale. We can model interaction of people as social networks, right? And at the scales of countries or even the entire world. So this social network metaphor is actually a typical one that when you think of a graph, you think of a system of relations and interactions between people, between users. And mathematically, the users of a social network are modeled as nodes of the graph, and their relations are edges or pairs of nodes that can be ordered. In this case, the graph is called directed, or unordered. In this case, the graph is undirected. And we can also attach some features to the nodes that will be modeled as d-dimensional vectors. Let's say the age, sex, birthplace of the users of a social network. Okay. We can also, of course, attach features to the edges, but let's consider, for simplicity, a graph that has only node features or node attributes. So the key structure characteristic of a graph or a set is that it is unordered. We don't have a canonical way to order its nodes. So when I number the nodes of the graph in this slide, I do some form of cheating. It is convenient because I can now organize the node features into a matrix of size n by d. So again, n is the number of nodes and d is the dimension of the features. But this way we automatically prescribe some arbitrary ordering. And the same holds for the adjacency matrix, which I can use to represent the structure of the graph, right? In this matrix, we have a 1 in position ij if there is an edge between nodes I and j, and 0 otherwise. And this numbering, the ordering of the nodes, prescribes us how this adjacency matrix will be ordered. So if we number the nodes differently, the rows of the feature matrix and the corresponding rows and columns of the adjacency matrix will be permuted accordingly. And we denote this permutation matrix by P. And P is an element of the permutation group of n elements. We have n factorial such elements in the permutation group. We can think of P, as we'll describe later, as a representation of the permutation group. You can actually see here another important thing, that the representation is different for different objects, right? So you see that the permutation group acts differently on vectors and on matrices. So if we want to implement a function on the graph that provides a single output for the entire graph, right? Like in our molecular graph example, where we try to predict a single value, let's say the energy of a molecule, we need to make sure that the output of the function is unaffected by the ordering of the input nodes, right? So no matter how I reorder the nodes of this graph, I want the output to be the same. So this is what we call permutation invariant function. If, on the other hand, we want to make node-wise predictions, it could be that the task itself requires node-wise output. For example, if we want, let's say, to detect malicious users in a social network, or if we use it as an intermediate layer in our deep representation learning, we want, in this case, the output of the function to change in the same way as the input, with the reordering of the nodes, or in other words, we want the permutation equivariant function. And again, we'll talk about these concepts later in greater details. So if you look at a typical graph neural network architecture, you hopefully will immediately recognize it is an instance of our geometric deep learning blueprint with the permutation group as our geometric prior. So we have typically a sequence of permutation equivariant layers that are often called as propagation or diffusion layers in the literature, and also an optional pooling layer that produces a single graph-wise output, like the energy of the molecular graph. Some architectures also incorporate local pooling layers, typically obtained using some form of graph coursing that can also be made learnable. And it's interesting that the history of graph neural networks is pretty old, and probably the first works, at least that I'm aware of, on learning on graphs, they can be traced back to the papers of, let's say, Alessandro Sperduti on recursive auto-associative memory, dating back to 1994. But the term graph neural network appeared first in a series of papers by the group of Marco Gori and Franco Scarselli in Italy, and they're often cited as the origins of the field. And there are many more papers on this topic. I would say that in the modern time, already after the explosion of interest in deep learning, it was the 2013 paper of Joan with Wojciech Zaremba, Arthur Schlam, and Jan LeCun that introduced spectrograph CNNs and really reignited the interest in this field. But if you ask graph theory experts, they would argue that graph neural networks are just a fancy name or incarnation of a graph isomorphism test called the Weisfeller-Lehmann algorithm. And it is a classical algorithm in graph theory that tries to determine if two graphs are isomorphic or have the same connectivity up to reordering the nodes. And this is a hard problem for which currently we don't have an algorithm that works in polynomial time. And the two authors were Soviet mathematicians and programmers. Andrei Lehmann was a programmer that was still in the 60s when they worked an exotic profession. And Boris Weisfeller was an algebraic geometer. And they proposed an iterative color refinement scheme that they also conjectured to solve the isomorphism problem in polynomial time. It does indeed solve it for small graphs up to 9 nodes, and Lehmann showed it computationally, but a larger counterexample was shown a year later in '69. So for a lot of time, actual complexity of graph isomorphism was unknown. I think only recently Babai showed that it can be solved in quasi-polynomial time. So it's a very deep and interesting set of problems in graph theory. And also interestingly, the problem that Weisfeller and Lehmann were working on in '68 was posed to them by the chemist George Vladuc. He probably deserves the credit of being the first to model molecules as graphs as early as in 1963. And I think in the West, it is Morgan that is credited with the eponymous molecular fingerprints. But I think Vladuc was a few years earlier. So in chemistry, surprisingly, similar algorithms were used from also as early as the 90s to represent molecules. And it's actually interesting to see these old papers as they give a good perspective. And for example, Baskin in his '97 paper describes a neural device for searching correlations between structures and properties of organic compounds that are invariant with respect to the numbering of atoms in a molecule, what I call permutation invariance. And they used an architecture that is analogous to biological vision systems, right? So this is 25 years ago. It would take another 15 years for deep learning to become a big thing. So it's interesting how these dots are connected in science and how many ideas are reinvented and reincarnated in different fields. And that's why there is deep and intimate relation between chemistry and graph neural networks. So the core operation of a typical GNN architecture is a local aggregation. We are looking at the neighbors of each node in a graph. And we take their feature vectors that together form what technically speaking is called the multiset. Because even though the indices of the neighbors are unique, the feature vectors are not necessarily unique. And in this example that I show here, we have the blue feature repeated twice. The two nodes have the same feature vector. So a multiset is a set where the same element can be repeated more than once. Okay, and now we try to aggregate these features together with the feature vector of the node itself. And I remind that it must be done in a permutation invariant way because we don't have a canonical ordering of the neighbors on a graph. And I denote this local aggregation function by phi. And by construction, it must be permutation invariant. And if we apply this phi at every node of the graph and stack the results into a feature matrix that I denote by f, we get a permutation equivariant function. So if I reorder the nodes, the order of rows in this matrix will be changed in the same way. So it is permutation equivariant. And the typical way this local aggregation function looks like in GNNs is that we have a permutation invariant aggregation operator. Typically, it's sum or a maximum, a learnable function psi that transforms the neighbor features, and another function phi that updates the features of node I using the aggregated features of the neighbors. And there are lots of nuances in how to design each of these components and a lot of flavors. So Petra will talk about it in much more detail in his lectures. I should just mention that in the most general flavor, we have this nonlinear function psi that depends on both feature vectors of node I and j, and its output can be regarded as a message that is sent from node j to update the features of node I. So that's why these architectures are called also message passing graph neural networks. So let me now talk briefly about grids, and we would like to interpret grids as a particular case of a graph. So for example, a grid with periodic boundary condition that I show here is what is called a ring graph in graph theory. And if we compare grids to general graphs, the first thing that we notice is that we have a fixed neighborhood structure, right? So each node has exactly two neighbors. And not only that, the order of the neighbors is fixed. And I remind you that in our general design of permutation equivariant function on the graph, we had to be permutation equivariant because our multiset of neighbor features was unordered, right? So in the case of grids, we actually do have a prescribed order of the nodes. We can order them sequentially, and therefore we don't need to be permutation invariant anymore. And if we choose a linear aggregation function, basically aggregating as a sum, we get what is called convolution. So this is the construction of weight sharing that I mentioned in the beginning. If we write convolution in matrix vector form, we get a matrix with a very special structure. It's called a circulant matrix, where we can construct it by taking a vector of elements. So these are exactly the shared parameters that are used in convolutional neural networks. And by shifting it cyclically, we append columns in this matrix. And circulant matrices are very special ones because they commute with respect to multiplication, unlike general matrix multiplication that is not commutative. And in particular, they commute with a special circulant matrix that cyclically shifts the element of a vector by one position, what we call the shift operator. So saying that circulant matrices commute with shift is just another way of saying that convolution is a shift equivariant operation. We can first shift and then convolve, or convolve and then shift. The result will be the same. And this statement appears to work in both directions. Well, again, we'll see it later in the lecture of Joan. That not only every circulant matrix commutes with shift, but also every matrix that commutes with shift is circulant. So we can define convolution as a linear shift equivariant operation. And I hope here you see maybe for the first time the power of our geometric approach, that convolution automatically emerges from translational symmetry. And I don't know how you studied convolution before, but when I was studying signal processing, it was given with a bit of hand waving as a formula just out of the blue. And this is also unfortunately how deep learning is nowadays taught. So I hope that here you see that it is a manifestation of a fundamental principle of symmetry. And again, we'll talk about it in more details. So here's another nice thing. We also know from linear algebra that commuting matrices are jointly diagonalizable, or in other words, there exists a common basis in which all convolutions amount to pointwise products. So they become diagonal matrices. And because all circulant matrices commute, we can pick up one of them for the convenience of analysis. And it's easy to look at the eigenvectors of the shift operator, right? And we can actually analyze them by hand. We can write down in closed form the eigenvectors of the shift. And surprise, surprise, we see that this is the discrete Fourier basis, or the DFT. So all convolutions are diagonalized by the Fourier transform. And the eigenvalues are actually given as the Fourier transform of the spectra of parameters theta that forms the convolution. And the relation between the convolution and the Fourier transform is called the convolution theorem in signal processing. And this gives us this dual way of performing convolution, either by multiplying by a circulant matrix that corresponds to sliding a filter along our signal. The typical interpretation of convolution as a sliding window, or in the Fourier domain as element-wise product of Fourier transforms of the signal and the filter. And on grids, this can be done efficiently because we have special redundant structure of this of the Fourier transform. We can compute it using fast Fourier transform algorithms. So it is interesting that in graph learning literature, some of the first works use this second way to generalize convolution by generalizing the Fourier transform to graphs. So you can, instead of considering the eigenvectors of the shift operator, you can consider eigenvectors of the Laplacian matrix or the adjacency matrix of the graph. And we'll see it more in details when we talk about deep learning on graphs. So let me now move to a more general case where our group formalism will be manifested in a more prominent way. And again, as we've seen, we can think of convolution as a kind of sliding window or pattern matching operator. In an image, this is done by basically by extracting a patch of pixels from different positions in the image and multiplying them by our filter. Okay, so if I were to formalize it a little bit, we need to define the shift operator I denote by T subscript U that shifts the filter that I denote here by psi to a position U. We also need an inner product. So this is what matches the filter to the signal. In this case, the image I denote by X. And if we do this shift of the filter and correlate it with the image, I get the convolution, right? So sometimes it is called convolutional correlation. It really depends on whether we reflect the filter or not. Doesn't really matter. Now, this is also a little bit of cheating because this is a very special case. Because here we can identify the translation group with the domain itself, right? So the translation group of shifts, we can represent every shift by a point on the domain. So the point to which we shift, right? But this is not the general case. And in general, we'll have the filter transformed by the representation of our group that I denote by rho. And the convolution or the group convolution will now obtain values for every element of the group. And we can easily show that this operation is equivariant under the action of the group. And again, we'll see it in more details when we discuss these notions of symmetry and group representations. So I will leave it to Taco to prove it in his lecture. But this also shows us that we must assume that these groups are somehow small. So if they're finite, then they have small number of elements. So we cannot do, for example, compute this convolution for a super exponential group like the group of permutations, or if it's a continuous group, it must be low dimensional. We cannot compute integrals on a 10-dimensional domain. Okay, so let me show you one example of a convolution on the sphere. So it might appear exotic, but actually spherical signals are very important in some domains, for example, in astrophysics, where a lot of observational data is naturally represented on the sphere. So our group here is what is called the special orthogonal group, SO3. So these are rotations that preserve orientation. And its action on the point, if we represent points on the sphere as unit three-dimensional vectors, the action of the group on the points can be represented by orthogonal matrix with determinant 1. Right, so positive determinant means that the orientation is preserved. I denote it here by R. So we have here the convolution. It's defined on SO3. So we get the value of this inner product for every rotation R of the filter. Now, one thing that you need to understand is that actually the input and the output domain structure is very different. So the sphere is a two-dimensional manifold, right? So the 2 degrees of freedom on the sphere are the longitudinal and the latitudinal coordinates, right? The azimuth and elevation. On the other hand, the rotations, we have 3 ways to rotate, right? So we can rotate along the parallels, along the meridians, and around the filter itself. So it's SO3 is a 3-dimensional manifold. It's a Lie group. It has a manifold structure, so it is continuous. And it means that if we want to apply another layer of such convolution, we needed to apply now on a domain that is SO3 itself. So the points on this domain are rotations. I denoted them by Q. Okay, and you can see that in this example of the sphere, it's an example of a non-Euclidean space, a manifold. And again, we'll be talking about manifolds in more details in, I think, in the 9th lecture. So don't be afraid if you don't know what a manifold is. You can roughly think of it as a kind of space that looks like a multidimensional surface. Right, so it is a manifold, but it is quite special in the sense that every point on the sphere can be transformed into another point by an element of the symmetry group of rotations. Right, so sometimes we say that the group has transitive action, and in geometry we call such spaces homogeneous, and the key feature is that they have this global symmetry structure. And this global symmetry structure doesn't always hold for general manifolds. And if we look at conversion on images, right, when we apply a sliding window, first thing that we notice is that it doesn't matter which way we go from one point to another, we'll always arrive at the same result, right? And this has to do with the fact that the image is flat and we can prescribe a global system of coordinates. On a manifold in general, the situation is quite different. Because of the curvature of the manifold, if I go along the green path, or if I take my filter and move it around along the blue path, I will arrive at a different result. So we call in differential geometry this concept the parallel transport. And roughly speaking, it says that if I move a vector on a curved surface, the result will be path dependent. So we don't have this possibility of take a filter and move it around a manifold as we did it on the images. Right, and again, we'll be talking about these concepts in much more detail later on, but just to give you a gist of it, the crucial difference between manifolds and Euclidean spaces is that manifolds are only locally Euclidean. We can map a small neighborhood of a point U to what is called the tangent space, and tangent spaces can be equipped with additional structure. For example, we can assign an inner product to them that is called the Riemannian metric, and it allows us to measure lengths and angles and volumes. And if we deform the manifold without affecting the metric, we call it an isometric deformation. And isometries also form a group. So it's called the isometric group of the manifold. And we can define an analogy of convolution of manifolds using a local filter that is applied on this tangent space. And if we make this construction intrinsic or expressed entirely in terms of the metric, we get deformation invariance, or invariance with respect to the isometric group of the manifold. And this was, in fact, some of the first architectures for deep learning on manifolds that we call geodesic CNNs. Now, one important thing that I didn't say is that because we are forced to work locally on the manifold, we don't have a global system of coordinates. So we need to fix a local frame at each point, or how physicists call it gauge. So I mentioned gauge theories in physics, so that's exactly the same concept that is actually a mathematical notion that simply describes a way of attaching a local reference frame to every point on the manifold. And the gauge can be changed arbitrarily at every point by applying what is called the gauge transformation that forms what is called the structure group. And the choice of this group really depends on how much assumptions we make about our domain. So a manifold on its own doesn't have much structure, so it's only a topological space. So there any transformation is possible. So in this case, G is the general linear group, basically an invertible matrix. I can transform completely arbitrarily two frames one into another. If the manifold has orientation, we can restrict the determinant of the transformation to be positive. If we have a Riemannian metric, right, an inner product, we can restrict the transformations to be orthogonal. So we have a notion of preservation of angles. And if we combine metric orientation, we can get the special orthogonal group of rotations, the SO2, if the manifold is two-dimensional. These are rotations that preserve orientation, as we've seen on the sphere. And so the gauge can be changed at every point, in this case by local orientation preserving rotation, and we need to account for the effect of the gauge transformation on the filter by making it transform in the same way. So the filter is gauge equivariant, and Taco will talk about this construction in more detail in his lecture. And you may wonder why at all we care about manifolds. They are pretty exotic things in machine learning. And the reason is that in computer vision and graphics, for example, manifolds or their discretization, usually in the form of meshes, are a standard way of modeling 3D objects. And what we gain from our geometric perspective is filters that can be defined directly on the object intrinsically, and this equips our deep learning architecture with invariance under inelastic deformations. And as you can see in this example, the intrinsic convolution is completely unaffected by the deformation, while the result of the traditional Euclidean convolution is very different. And one application where dealing with deformable objects is crucial is in different applications in computer graphics and vision, such as motion capture or mockup. And you might have heard or seen mockup in the production of expensive blockbuster movies such as Avatar. And what you see here is a cheap markerless motion capture setup from a Swiss company called Phase that was acquired by Apple 6 years ago. And now you see the incarnation of this technology in on the modern iPhone that is produced by Apple. And geodesic convolutional neural networks and geometric deep learning in general were used in these problems to solve the correspondence problems, right? That brings the noisy scanner input to some canonical representation, the mesh of the face of the or the body. And here you can see some old results from a paper where we used these architectures to solve a nearly perfectly correspondence between shapes. And more recently, it is also possible to use these architectures for 3D shape synthesis. This is an example of a demo that we showed in 2020 at CUPR. That was a collaboration with a startup called Real AI. So this is faster than real-time 3D body avatar with detailed hands. And the company was acquired by Snap last year, so you can already see it in Snap products. So geometric deep learning, and in particular graph neural networks, have really become ubiquitous in a broad range of problems and applications. So really, as Peter calls them, the first-class citizen of machine learning. And you can find instances and applications of geometric deep learning practically everywhere in very exciting fields, from self-driving cars to navigation problems such as predicting accurate arrival time in Google Maps. So Google actually uses graph neural networks in their product, in Google Maps, solving combinatorial problems of, for example, component placement on a silicon chip, which is a key problem in designing future generations of silicon, detecting events in particle colliders in high energy physics, understanding the structure of proteins, problems such as protein folding, or predicting protein binding, or designing new drugs, for example, antibiotics that will be able to cope with antibiotic-resistant bacteria. So let me recap what's in store for this course. We'll try to see that symmetry is a fundamental principle that underlies a lot of design choices in deep representation learning. We'll try to focus in this course on a set of fundamental principles based on the concepts of invariance, equivariance that we'll express through group theory. We'll see that this is a very general design that can be applied to different types of geometric structures and different problems. And in the next lectures, we'll introduce gradually all the mathematical formalism that will allow us to cope with these concepts. And we'll see how they apply to particular instances of different domains, sets, graphs, grids, homogeneous spaces, manifolds, meshes, geometric graphs, more general concept of gauges and fiber bundles, and sequences and temporal data. So I think I will stop here. Thank you very much, and please let me know if you have any questions.